start the discussion, in the morning session we had two talks. One was on role of observer in collapse, and the second one was more gravitation-induced collapse. And as the protocol we are following, we first call upon the students, and I will just go one by one. So the first question comes from Shashwato Sen. Can you please come to the podium here and place your question, please?
Hello. So my question is to Professor Singh is, in the trace dynamics, like your variable is a matrix. So is there any relation to random matrix theory?
I'm not an expert. Does that work within the framework of quantum theory?
Yes, so you have a matrix valued path integral.
No, random matrix theory is within
the
quantum theory domain, is it?
Yeah.
So, I mean, I don't know enough about that to answer, but you know, the philosophy of trace dynamics is that it is not quantum theory. It's matrices, yes, but it is like you are as if you are doing classical mechanics or classical dynamics with matrices. But that is already very non-trivial because of that extra charge, new charge that I showed, which Adler found with his student. This charge is not there in classical mechanics, and that charge is what distinguishes classical mechanics and trace dynamics, making trace dynamics more general than quantum theory. You have classical mechanics, quantum theory, and trace dynamics. So about random matrices, I really don't know. If you see Adler's book, by the way, if you want to learn about trace dynamics, there's a very nice book by Steve Adler, written around 2004, Cambridge University Press. It's called Quantum Theory as an Emergent Phenomenon. So the work was done by him with his collaborators in the 90s, and then he wrote this book. So you can see that. When following that book, I did not come across any comparisons with random matrix theory. But I mean, that's also my ignorance. I'll look it up and try to find an answer.
Just a follow-up question.
Please.
Yeah, so just wanted to understand, like maybe you said, I missed it. So what are the constraints on the matrix? Is it has to be invertible, Hermitian, or something like that?
Not restricted to be Hermitian. What is more important is the entries are Grassmann numbers, because that allows you to describe fermions and bosons. So take any trace dynamics matrix with Grassmann number valued entries, Q, write it as QB plus QF, where QB has entries that are Grassmann even. That is, they are product of an even number of Grassmann elements. QF are Grassmann odd.
Right.
So the QF, the Grassmann odd elements will anti-commute with each other. The Grassmann even will commute with each other and with everything else. So, and hence the symmetry versus anti-symmetry. So Grassmann even trace matrices are called bosonic, what I call QB. Grassmann odd are called fermionic, the QF. A priori, there is nothing is said about, say, their dimensionality, and that's about it. You allow for the overall Hamiltonian to not be self-adjoint. That, in principle, there's no reason. I think when you go beyond quantum theory, why should the Hamiltonian be self-adjoint? I mean, only when we come to the world that we know, which is described by quantum theory. But if trace dynamics is being assumed to hold at some domain where quantum theory has not yet been tested. You see what I'm saying?
Yeah, I'm following. It's okay. So, so what I get is that it's a priori there is no constraint. Like whatever happens, Like after doing the
so
dynamics.
as I said, Adler does not specify a specific Lagrangian. He left that for the future. That's what we are trying, to make a specific Lagrangian motivated by the use of the spectral action principle, namely the general relativity action is trace d square, where d is the Dirac operator on the manifold. And the Dirac operator can also be written as a gradient operator on a quaternionic or octonionic space. So that seems very promising. So d square is like kinetic energy, it's like the square of the momentum. Yeah. So we are trying to construct a Lagrangian, and so we have freedom. We don't restrict it to be the Hamiltonian to be self-adjoint.
Thank you.
Great. Obviously, this question was exclusively for Professor Singh, but in case Howard wants to make some comment, please go ahead. Is there any?
Can you? I am on.
Yes, we can hear you.
Yeah. No, I don't think I. Sorry. Okay. No, I don't think I have much to say on that. Sorry.
Okay. We go for. So now we go for the next question, and yeah. So the next question is coming from Amrapali. So I will request whenever you place your question, also mention the institute or university you are affiliated to. Please go ahead.
Hello, I am from ICTQT Poland. So, very nice talks, both of you. My question is for Professor Howard. So, I am a bit confused about the definition of absoluteness of observer, because when you formulate the local friendliness theorem, you talk about probabilities. But when you talk about the Coates graining of the Bell's theorem, you mention that the observers is absolutely a real event, not relative to anything or any world. So like for example, if you think about quantum reference frames or any unitary transformations, so the observables are also unitarily transformed, and so as the states. So like the probabilities still stay conserved because you trace, you have the unitaries inside the trace. So that would fit in the local friendliness description of this absoluteness, but not in the Bell's Coates-Green scenario. So would that not be like one of the things we would like to discard from the definition, or am I missing something out?
Okay, that's quite a subtle question. Can I share my slides again?
Yes, please go ahead.
Able to do that? Yeah. Okay. Did that work? No.
We don't see yet. Maybe it will take a bit of time.
It's not letting me.
Well, it's the same procedure as you used during the talk.
Doesn't seem to be. No, it's not letting me share. Don't understand that.
You see the place where you have to click in order to share?
I can see I can see the up arrow, but and I clicked on it before and it seemed to work, but now it's gone grey, suggesting that I can't do it. I don't know why. Yeah, it's just not letting me do that.
Well, I think
Oh.
it's here, so.
Oh, okay. All right, now it's letting me do it again. Let me try it again then.
Oh, this control, post control. Yes, sharing screen is
Yes, okay, now that it's working. All right. I think, yes, you can. Maybe not. Right, okay. So let's see if I go. So you're asking about the Bell's theorem, right? This
Yeah, the previous slide that
formulation of Bell's theorem. So I think this. Yeah. So
Yes.
so when you said coarse grain, did you actually mean fine grain?
Yeah, fine grain, sorry, yeah.
Fine grain, right? Yes. Okay. Okay. And so your question is about absoluteness of observation.
Yeah.
So I guess to maybe one comment I'll make is that it's not about observables, which is a concept in quantum, in the mathematics of quantum theory. It's absoluteness of observation once they are, an observation means the result of an observation.
Okay, so here you also indirectly mean about the probabilities.
So this is not a statement about probabilities, except insofar that if you have a collection of things which are absolutely real, then there must exist a joint probability distribution over those things. Now, of course, that there's a lot of assumptions. Yeah, arguably there are some assumptions about questions you could ask about what do we mean by probability. But I mean, in the context of a repeatable experiment, if there is a variable that we use to consistently label an outcome or a setting or whatever in a repeatable experiment, then we can think of probabilities just by considering an ensemble of those experiments, and then I don't think we run into difficulties. So, saying something that's absolutely real, if I have a bunch of things which are absolutely real, as I said, I think that means that we can talk about the joint probability of all of those things. That's the connection between the absolute reality and probability. Does that answer your question?
Yes, very much. Thank you.
Okay, no, great, thank you.
Thanks, Howard, as well as Amrapali. So we'll go for the next. By the way, in case you have some comment to add, also please raise your hand and we'll accept that. So our next question goes to Sagnik Ray. Are you there? Yeah, please.
So my question is for Professor Howard. I am from ISA Trivandrum. In the context of the standard Wigner's friend scenario, so there is friend inside a room performing some measurement on a quantum system, and there is Wigner outside, who is a person with like a human thinking capability, but with superhuman technology, so that Wigner can use any kind of unitary on the friend plus system, super system.
This is the way that Wigner and the friend are commonly talked about these days, although not the way Wigner talked about it originally. But yeah. So,
right. Yeah. So now what I was thinking is, if now I put Wigner, friend, and the system inside another box, and now there is a super Wigner outside, and so now I can iteratively go. So keep on putting people inside boxes, such that if I extrapolate it to its logical conclusion, there is only one person outside and the entire universe is in one box. And this one person outside thinks like a human but has superhuman technology, so that this one person can apply any kind of unitary inside all those boxes. So aren't we going dangerously close to kind of super determinism? Because now there is a huge unitary according to which the majority of the universe can be evolved, and there is only one person determining what to do with it. Obviously, we cannot go outside the universe. I'm positing there is no person outside the universe who is doing that. So there is not super determinism, but we are dangerously close to it.
Yeah, I'm not sure I would say that it's super determinism, but well, I don't know. I guess it depends on what you're imagining what's happening inside the box to be. If it's just standard quantum dynamics happening inside the box, then I don't think there's any reason to call it superdeterminism or even determinism of any sort. It's unitary quantum evolution, right? And it comes with the problem, the quantum measurement problem or the quantum reality problem. So it's not suggesting to me that, it just raises a whole heap of questions. If the question is can we know that that's not the case? How do we know that we are not in the situation of being a friend and that there is some enormously powerful being, that we're actually inside of the universe that we see is real, but it's inside some box, and somebody could decide to reverse its evolution at some point, or maybe they already have. That we can't logically rule that out, I would say, but I would also say that there's absolutely nothing in the laws of physics that we know about that would suggest that that is possible. In other words, I think we can essentially, like there's no super observer that we could conceive who uses the laws of physics we know about, who would be able to, reverse a universe of certainly like something of the scale of our observable universe. I mean, but even something much smaller. Even if I was just literally, yes, in a box the size of my office, I think it's fair to say that it's not conceivable in the laws of physics that we know that somebody could actually reverse the evolution of that. So that's why the role of an artificial intelligence is so key to the way I envisage an actual big friend experiment would work, because then it's still an extremely challenging experiment to imagine, but at least it's not something that's inconceivable by the laws of physics as we know them. Does that answer your question?
Yeah, so actually this point struck because yesterday after the post-lunch session during the discussion time, I think Professor Manik was the one who suggested the Wigner-Friend scenario, and then there was someone else who pointed out that in the Everettian concept there is like a universal wave function, so it's the entire universe is evolving under unitary dynamics, so there must have been certain kind of initial condition which is determining everything that we are doing right now. So,
well, I don't know if determining doesn't sound like the right description to me, in the sense that if the Everettian picture is right, then it's not one thing that I'm doing right now, right? There are countless worlds where there are different versions of me doing different things. So it's sort of hard to think about that as meaning that it's determining that I'm doing the particular thing that I'm doing. But in the sense that, like what I'm doing is just in the space of the possibilities of things that, I could be doing. Well, yeah, okay, that's determined by the wave function. That's true. So one could argue about does the Everettian version, is it? It seems to me that you're getting at some sort of problem of free will from the fact that you mentioned superdeterminism before, and one can ask the question, like, does an Everettian picture, is that more problematic for free will than a deterministic universe, or is it less problematic? In my mind, I don't think it really makes that much. It doesn't make that much difference to my mind. But I think there are other problems with the Everettian interpretation. So there would be other reasons that I would be worried about that. But I don't think that we can rule it out on the grounds that we want to have free will, as opposed to. Unless we also want to rule out any deterministic theory as also being that we also want to rule that out because it would be incompatible with free will. Does that answer your question? Or at least give some idea, of my opinion? Okay.
Actually, Nicholas has one comment to make. So, Nicholas, please.
Yes. So indeed, I disagree with Howard on that one, and I wrote actually a short paper arguing that many worlds is incompatible with free will. So maybe you can find it on the archive.
Sure. Thank you, sir.
Thank you.
Well, maybe I'll just say, I'm not saying that it is. I'm just saying I don't see any difference between it and a deterministic theory like Newtonian mechanics, for example. I can't. It's not obvious to me that Everettian is more problematic or less problematic for free will. Yeah.
Okay. Thank you. So now I will call upon Surajit Saha. So you please also introduce yourself. Just mention the institute.
I'm Surajit from Calcutta University, Kolkata. My first question is for Professor Howard Wiseman. The question is regarding the mathematical equations of your many interacting world paper.
Oh.
In that theory, for finite number of world, predictions deviates from quantum mechanics. But as time progresses, the deviations increases. Now, I am curious to know that whether you investigate incorporation of stochasticity in the equations. That is, whether incorporation of noise solves the problem, that is, as time increases, deviation from quantum mechanics remains bounded.
Okay, so so to be clear, so this is a question about an approach to quantum mechanics that I think was mentioned in the introduction about what I've done, but not something which I talked about at all in this talk. And maybe to make the point, it's not one of the interpretations that I listed here, and that's partly because it's I wouldn't even call it an interpretation. That's why I deliberately called it an approach. Because it was an idea that we thought had promise. I don't think it's been developed to the point that you could see that it's an interpretation. Partly because of the problem that you just said, that for any finite number of worlds there are going to be deviations from quantum predictions, and in fact those deviations grow exponentially. And it's not clear that it would ever be an adequate empirical theory. So to answer your question, no, we never considered adding stochasticity into the theory. I don't have any intuition that would make things better, but of course I don't know. There are, because in the sense that it's very similar to Bohmian theory, there are of course stochastic versions of quantum theory.
Yes.
The name is escaping me, but which are reduced to Bohm's theory in a particular limit. So it does, I'm not. It sounds like it could be a sensible thing to consider, where maybe the stochasticity is at the level of individual worlds, but the non-locality comes from the interaction between worlds. But I just don't know about that. Yeah, it's an interesting idea, but we certainly never investigated it.
Okay. Now my next question is for Professor T.P. Singh. I could not understand how the pre-space-time structure deals with quantum non-locality. Action at a distance is still there.
Okay, this needs something to be said carefully. I have few comments to make. Pre-space-time is non-commutative. Yeah, it doesn't have the commutative structure of ordinary real numbered space-time. So in that sense, it is inherently non-local. Non-commutativity means this point is not separate from this point. You cannot define it that way. There is a Lorentz invariance, but there's a Lorentz group which would keep, that symmetry is there in, say, maybe a higher dimensional space-time. That by itself does not necessarily imply a causal structure, which is related to having real number valued space-time. So having non-locality is not a problem. So whereas I am right now thinking of non-locality in 4D space-time as being effective. If you give me a 6D space-time with 3 time directions, it can happen that the situation there is local in the bigger space-time, and projected to the smaller space-time, it would become, it would look non-local. So at this level, I think I don't have a problem. The more serious question to consider, maybe I want now Nicholas also to comment on this. If I have underlying theory which is deterministic and non-unitary, it breaks superposition. Does that imply that I have a problem with Bell's inequalities? I'm not clear right now. One thing is that this is a statement about the underlying theory, which is not a hidden variables theory. You coarse grain the underlying theory to get quantum theory. Quantum theory has randomness, it has indeterminism, so you will get the standard picture of Bell's inequalities. But what is the underlying theory doing? It's a deterministic theory, but it is not separable. So in the previous talk, separable predetermination is a problem with experiments. But what about non-separable determinism? So to me it looks that that may be okay, but I think, Nicholas, you know these things better than me. Yesterday we didn't complete the discussion, now you have heard me talk. I want your feedback on if the underlying, so as I said, it's like Brownian motion as an underlying atomic theory. The underlying atomic theory is not a hidden variable, so it's at a higher level of graininess where more information is there. Bohmian mechanics hidden variables are at par with quantum theory. They are not an underlying theory. So those are my thoughts. So now I want you to please comment on this.
Yeah, Nicola, please.
Okay, well, thank you. Actually, I wanted to ask questions, so maybe I ask the question because it follows up on what we just heard. Indeed, so the day before yesterday, we had this discussion in public, also in private, and you said that with this free time dimension, things go on there locally, but then projected onto our four-dimensional space-time, you have this apparent non-locality. And I understood that you were also saying that if we do this perfect timing in a Bell inequality scenario, we would not violate Bell inequality, so we would violate quantum predictions, which is, of course, highly interesting. But what I don't understand, and still don't understand, I'm sorry, is in which reference frame should we perfectly time such a Bell test?
My understanding was that any frame should be good enough, either the Ellis frame that you showed with, or the Bob frame. I mean, it should come out.
But whenever we do a Bell test which is space-like separated, there will always be one reference frame in which the timing is perfect.
They match, you mean?
Well,
Perfect?
you know, if we are space-like separated, any space-like separated events are synchronous in one reference frame.
That is a good point. Oh, yes. If in that case the only way out is to go to a preferred frame like the CMB rest frame, there is at least a preferred time in this theory, that so-called Cohn's time, which is an absolute time which should be oblivious to this kind of synchronization. Thanks for bringing this up. I had not thought of this. So the Cohn's time and the CMB rest frame would go well with each other. I need to think more. But I also want you to, no, you complete first, then I'll...
Yeah. So, because then the next obvious question for an experimentalist is, how good in practice should this timing be? Let's say
yes.
Is that something where your theory makes a prediction or not yet?
Yes. Sorry. Yeah. After talking to you the day before, I tried something. The answers are pessimistic. It would be in your picture of faster than light. If I go to that language, it would have to be 10 to the power 40 times the speed of light. So your bound is, I don't know, 100?
100,000 times the speed of light. So you said 10 to the 40?
Yeah, so that number is coming. This is the first guess.
Wow.
I could be wrong.
Okay. Harald, you have some work to do.
So this is the first guess. It is coming from knowing the relative strength of the gravitational and the weak interaction. So if the weak interaction is governing the geometry of those extra directions, they ought to obey that, that the weak interaction is very short range. And so the way this estimate goes is, let us look at how big is the universe in Planck units, 10 to the 28 by 10 to the 33, about 60 orders of magnitude in Planck units. And one can make an argument that in the additional dimensions, it should be a cube root of 10 to the 60, about the 20 orders of magnitude in Planck units. That is around 10 to the minus 13 centimeters. That's the Hubble radius. And now that takes 10 to the minus 23 seconds to cover. Anything shorter would be even faster. So,
maybe just to continue on that, of course, this is not feasible experimentally, not today and also not in the coming century. But is that a prediction of trace dynamics in general, or is it a prediction of your specific model of trace dynamics?
Yeah, it's my specific model. Adler actually goes into a detailed discussion of Bell non-locality in trace dynamics. He's very careful. He's aware of the Bell inequalities. What we didn't complete yesterday. What is your feedback on that?
Well, I'm not sure I know, but maybe there's another point which I don't understand about what you said. You said by doing some coarse graining, we get out randomness. Mm-hmm. But usually coarse graining means making some averaging. And by averaging, we, on the contrary, average out randomness to get more determinism. Now here you average determinism to get out randomness. I don't understand.
In the sense that I know less. Suppose, let's take the time of arrival example. Suppose capital T, suppose is Planck time, and within a Planck time, enough things are happening. Thus, depending on when you arrive, you will get a different interaction with the measuring apparatus or the environment. But that interaction will be deterministic. If you average and you don't know when exactly you arrived, depending on when you exactly arrive, different outcomes might be happening. And it appears random because you didn't measure your time of arrival precisely enough. If you arrived at T1, the pointer would have gone to the left. If you arrived at T2, the pointer would have gone to the right. But both T1 and T2 are within an interval delta T, which is your resolution. T1 and T2 are smeared out to be the same time, in this sense.
Yeah, thank you. I don't think I have more to say on that today. Maybe we continue with the junior guys.
Before I move to Surajit, Howard is also here. So Howard, if you want to make some point, particularly some additional question or answer to what we have discussed now.
Yeah, I could pose it to you as my lack of understanding. You said...
Sorry, I can't, who's talking?
Can you hear me? Or you can't hear me?
Can you hear us?
I can hear, yeah, but who's talking?
Yeah, so can you place the question once again?
Yeah, you mentioned...
Can the camera be moved? The camera is on Nicola, which is... not very nice, but...
Can you, please turn the camera in this side, please.
So you said separable predetermination is contradicting experiment. So suppose I have non-separable predetermination. Am I okay with that?
Yeah, so this is the phrase that Bell uses. So Bell's first paper, he uses a lot of different terms, and it's not completely clear what he's talking about. But it seems pretty clear to me that when he uses the word separable here, he just means the same as local, in the sense that the term is later been used as. So I know people definitely like to use the word separable to mean something different from local because they don't obviously have the same meaning. And there are many different ways of discussing the assumptions in Bell's theorem, but definitely in his 1964 paper, all he meant by that was locality, in the sense, I think, that one party making a measurement choice can't affect the probabilities of the outcome on the other side in the context of the theory. So even given whatever variables exist in the theory. So I know so you maybe are thinking of your trace dynamics, well, Adler's and your work on trace dynamics, maybe that's non-separable in some other sense. I don't know. I mean, I guess that would be a question whether you think that it is just a non-local theory. Would you say that it is the case in that theory that Alice doing something here can lead to something changing on Bob's side? It sounded as if that's from your discussion with Nicola that you think that is the case and that it can happen faster than light, in particular at some very fast but finite speed. So is that correct?
Yeah, so for me also, non-separable means non-local. I agree with you.
Okay.
The question was about predetermination. How non-local predetermination, is that a problem, let's say, with the experiment? I'm non-local, all right, but I have...
Yeah. No, so I think Bohmian mechanics, for example, is the best known example of a theory which is non-local but predetermined in the way that Bell was talking about. And Bell even refers to that in his 1964 paper as a motivation that we know that we can have predetermination in the theory, but it has this, horrible or something, I don't know. He uses some word about gross, that's right, grossly non-local behavior. And that was motivation for his theorem to say, well, is that necessary? Is that non-locality or non-separability necessary? And then he proves that it is actually, yes, if you want to have the predetermination.
Okay, thank you. Yeah, thank you. Thank you.
Thank you, Howard.
Yeah.
So, Surajit, you may continue, but be a little quick.
Okay. And my last question is, how many worlds deals with non-locality?
Whom you were asking to? Both the speakers?
Both the speakers.
Okay, please. I think, Howard, you start, maybe?
Yeah, please go ahead.
Sure. Yeah, this is a very difficult question that we started, Eric, when I say we, Eric Cavalcanti and I particularly started struggling with in writing the local friendliness, the thoughtful local friendliness paper, and decided that, yeah, we weren't going to come up with the definitive answer for that, and so we sort of put it off for a longer paper that will sometime get written. I think the many worlds means many things. Depends on which version of many worlds I think that people have in mind. I mean, exactly what a world is, how literally one takes them. So there are definitely some people who would broadly classify themselves as many world believers, who would say that there is nothing non-local in the theory, that it's a completely local theory. Personally, I find these accounts unsatisfying, unbelievable. I think you can only think like that if you're not thinking of worlds in any serious sense. I think that if you seriously think that it's a theory of multiple worlds, then it just has to be a non-local theory. And that if you say that it's not a local theory, then you're really taking a more operationalist and view or relativist view, where it's really just a theory about what I'm experiencing. And I think that's not well, okay, then we get into the question about what is many worlds even the right name for the theory, because the theory, that the name that Everett gave to it when he published it was a relative state interpretation. And that sounds a lot more like it's just talking about what things look like relative to a single observer. And when you look at it like that, it's not that far away from the cubist perspective. So I think there are many ways of looking at many worlds, and but I would say that, yeah, if you take the idea that it is actually a theory of worlds in any way seriously, then I think it has to be a non-local theory.
Okay. Thank you, Surajit.
Can I say something?
Yes, please,
Yeah.
please.
Yeah, so maybe I have a slightly different view. I don't know if I'm not saying I'm right. So the sense of quantum non-locality is collapse of the state. Collapse happens at Alice's end. The influence is felt at Bob's end non-locally. That's the problem. That's a puzzle, let's say. To my understanding, in many worlds, there's no collapse. So I can't see, if there's no collapse, why is there a non-locality puzzle? Let's look at it in two steps. The many branches of the universe, which are parallel branches. In my branch, there is one copy of the state, but all copies of the state are coexistent. There is no collapse happening. And quantum field theory as such is a local theory. Those rules should continue to hold because the entire set of parallel universes is obeying quantum theory. So there's no collapse and hence no non-locality. That would be my understanding. I could be wrong, but Howard, do you want to say something?
Yeah, so I could respond to that. So I guess the reason I would say, you're absolutely right, there's no collapse, but if we take many worlds seriously as the theory of many worlds, then we have to say something about when does a world split into other worlds. And I think it's that timing of that split which then raises all the same questions as the timing of collapse. And if we're actually thinking of that as actually being, worlds are really things that exist like our world, some sense there's something happening in three-dimensional space, then if a world splits into two worlds, then that has to be something that happens instantaneously over the entire universe. And in my book, that looks like something non-local. Now, of course, there'll be some people who describe themselves as many worlds who would say, oh, you're thinking about that all wrong. It's not a literal splitting. The worlds are just some sort of metaphorical thing. There's no literal. And then I'd say, well, what is your theory actually about then? Like, what are you really talking about? And I think this is one of the problems with the Everettian or many worlds interpretation that I have. Yeah.
I agree. I want to use this opportunity to open my mouth about many worlds. I didn't say anything. The world that we live in doesn't look like the world of many worlds. It's at least that's my naive picture. And they say that you cannot see the parallel branches because interference has been destroyed between the branches, so you cannot see them. But if I cannot see them, how do I know that they're there? And the biggest problem, which a lot of people have mentioned, to me is that if there is no collapse, where are the probabilities coming from? Why are all the branches not equally likely? And then one goes into a lot of something called frequentism, etc., to try to derive the Born rule in many worlds. And for me, that's not a comfortable situation. I would much rather have dynamical collapse in one world. At least it's a falsifiable proposal, unlike many worlds. So they say that they have extravagance of universes, but an economy of postulates. Collapse models has economy of universes, but extravagance of postulates. The experiment has to decide which of these is correct, and at least collapse models are falsifiable.
Thank you all three of you. The next question actually comes from Shreya. Are you on the audience? Yeah, please.
I'm Shreya J. I'm from Niger, Bhubaneswar. My first question is to Professor Howard. In the Alice, Bob, Charlie, Debbie protocol, when if Alice say doesn't get x is equal to 1, then the idea is you go back in time, you throw Charlie away, and then then Alice will do the experiment on her own. understand why maybe there's some lack of understanding here from my part, but why do we have to go back in time to do that? Why can't we just be like, okay, fine, we didn't get X, we'll do another preparation, similar preparation, and then this time we'll just allow Alice to make the measurement directly instead of letting Charlie do it.
You have to unmute maybe. How about we cannot hear you? We cannot hear you.
You
have to unmute yourself.
Leave a message.
Sorry, I was muted all that time.
Please,
sorry. Okay, let me try this again. Is that working?
Yes, it's coming.
Okay, so sorry about that. Okay, so your question, sorry, I was having a bit of technical trouble, so I didn't catch all your question, but it was about this type of protocol, yes? And so your question was, why is it necessary to reverse time? And maybe I should, reversing time is probably, it's really a logical reverse, or it's a dynamical reversal of what's happening inside this box, is a better way to say it. So what exactly was your question about it?
The question was, why do we have to reverse the time? Why can't the preparation be made again, and then Alice can just directly check the qubits?
So you mean just re-prepare the entangled qubits, but not involve Charlie at all?
Yeah.
Yeah, okay, good question. Because... yeah, okay. Yeah, I should have a quick answer to that, shouldn't I? Let me think. Right, in that case, right, if we re-prepare with a new pair of qubits, then that means that Alice will have to... I think it's going to violate the locality, like the space-like separation, because okay, I hadn't thought exactly about this question before, but it seems like if Alice wants to do a measurement on a different qubit, she sort of has to let Bob know, okay, this run of the experiment we're not going to count. We have to run it again, and I need some new qubits. So that's like opening the efficiency or detector loophole in a Bell experiment, right? If you throw away some runs of the experiment, then you open a loophole, and you can violate the inequalities without. I mean, you're not properly violating the inequalities. So it has to be that every run of the experiment you get an outcome. It can't be that you just say, oh, okay, no, this time I want to do something different. So even in a standard Bell experiment, Alice and Bob, if you want to do a loophole-free experiment, every time they prepare an entangled pair, they have to generate an outcome.
And I have another question to Professor Howard itself. It kind of follows from a previous question, but when the time reversal thing was done, I believe that it was done for Alice as well, like the whole system was time reversed, right?
Everything inside the box is time reversed, in this
Just
picture.
inside the box, not like Alice is like...
So Alice herself is completely unaffected, yes. So Alice is just pressing, okay, it's not a great picture here, but Alice is like doing some control to tell, time to go backwards, so to speak, inside this box where Charlie is. So she's a super observer for what's inside the box, but herself, nothing special is happening for herself.
But won't it create some paradox in the sense that she can, do again wherever she whatever she wants? They can just reverse the time, do it and get the result she wants, and that's how the world will work. Again, the question that was asked earlier about superdeterminism.
Okay, so you could say, well, couldn't she just implant any memory that she wanted in Charlie or whatever and get whatever results she wanted. Yes, perhaps, but that's actually giving her a lot more power than is necessary to be able to reverse time, which is what I actually particularly like about this way of explaining what the superpower is, rather than making, as in the Časlav's version and the Fracke-Renner version, which involved making a superposition measurement. Because the point about this is that Alice doesn't actually need to know anything. So thinking about the the case that we the real experiment, so to speak, where Quali is we replace Charlie by a quantum computer. Alice doesn't need to know anything about the internal state of Quali. She doesn't need to know anything about his thoughts or beliefs or anything like that in order to be able to run the process in reverse. There's just an algorithm happening, an artificial intelligence algorithm happening, and Alice can just press a button that says, okay, now whatever gates, because we're talking quantum language, it has to be quantum, whatever gates have just happened on this process, and now run all of those gates in reverse one by one. But that doesn't mean that Alice knows what state it gets back to at the beginning. All she knows is that whatever state Quali is in is unentangled now with Q1, this qubit, so Q1 can come out and be measured by Alice. So it is still, so in the sense of, does this violate Quali's autonomy? In the sense that he's going to lose 1 second of memories. This is a genuine thing to worry about, and this is why I said, Quali would have to give permission for an experiment like this to be done. But it doesn't mean that Alice is just, Quali does not become an automaton in, well, not even an automaton, a puppet. He does not become a puppet in Alice's hands that, Alice is implanting things in or anything like that. Does that make sense?
Kind of. Yeah.
Okay, maybe we discuss later on.
I have one more question.
One more?
To Professor Singh.
It's a quick one?
Yeah, it's a
Please go ahead.
Is there something intrinsic about collapse model that makes it relativistic non-covariant?
Maybe I'll leave this.
That makes it?
The collapse models are not relativistically covariant, right? So is there something intrinsic about them, or is it so that we haven't found a proper collapse model which is relativistically covariant?
The initial proposal was, GRW proposal, was for a non-relativistic theory. Then many attempts were made to try to make them relativistic, Lorentz invariant. Henrik mentioned some of it. I know only a little bit. These generalizations run into difficulties at the level of the formalism. But my picture, which I mentioned briefly, is that if you want to make a relativistic model of collapse, there ought to be spontaneous collapse in the time variable also, not just position. So that is then collapse in space-time. But for that to happen, you have to raise time also to the status of an operator. That all takes us beyond quantum theory, it takes us beyond special relativity, but that is how I think it should be. There should be collapse in space-time. That is the only way I can think of a relativistic collapse theory. Treat space and time at par. So collapse in space-time means the pre-space-time is an operator. And I find that very interesting. Collapse in pre-space-time gives rise to space-time. So I'm quite happy with that.
Okay, thank you. Our next question is coming from Devashish. Are you on the audience? Yeah, please.
Yeah, so I'm from ISAR TVM. Yeah, so I have two questions, and
keep the mic closer to your mouth.
To Professor Howard. So my first question is that here, in this case, in this local friendliness theorem, so Alice has two choices, like x is equal to 1 or x not is equal to 1. And if x is equal to 1, she opens up Quali's lab and asks, but see as observed, right? So,
or in this case, just opens the envelope, so to speak, and looks at it, yes.
yeah. So that means that Alice actually measures something on the entire lab. On the combined system of Quali as well as the...
Well, okay, well, have a look at the cartoon which I've drawn here. So what Alice does is open an envelope and look at what's written.
But theoretically, that is actually a measurement.
Okay, yes, you could say that is... So, if one believed that humans caused collapse and nothing else caused collapse, then your description would be that Quali remains and the qubit and everything remains in a superposition until Alice opens the envelope and looks at it, and then his wave function will collapse.
Yeah.
Yes.
Yeah. So, so my question is that, for example, Quali is measuring, let's say, the sigma z on the spin of the entangled particle, and then this measurement by Alice basically means that Alice is also measuring in the same basis, but not only on the spin, but also on the combined system of spin as well as the entire lab of Quali, right?
Well, she's measuring an observable which is correlated not only with the spin but also with the other properties of Quali. Yes.
Yeah, but importantly, it should be in the same direction.
Same detection. What do you
mean?
Direction. Well, but no. But she is just reading a message from.
Yeah. So
from Quali. So she has. So yes, it will be. I mean, if Quali has actually measured in the sigma z direction, then he has no option but to tell Alice about the result in that direction, because he doesn't know the result in any other direction.
Yeah. So that is my question. So, like here, are we invoking some argument, a theory-dependent argument, in the proof of this theorem? Because now Alice. So if Quali tells the result to Alice, that actually means, from Alice's perspective, it actually means that Alice is measuring something and gets an outcome, right? So, and that measurement, that measurement has a description in the theory, and
yes.
And that measurement should be a particular measurement, because. So my question is: are we invoking some theory-dependent argument?
Right. There is theory dependence in predicting what an experiment like this will yield, right? Well, we are trying to avoid theory dependence in the derivation of the inequalities that will be violated according to that prediction, right? So quantum theory obviously has a role in predicting what will happen when we do this experiment. But the inequalities which we're going to violate, we're trying as hard as we can not to mention quantum theory at all in the derivation of those. In the same way that in Bell's experiment, Bell's theorem, right, the derivation of Bell inequalities has nothing to do with quantum theory.
Yeah. Okay. I mean, yes. I mean, yeah. But yeah. So but here, what I'm saying is this, that I can imagine a strange theory where this is not possible. I mean, telling the outcome of the measurement, that what Quali has observed to Alice, may not be possible. I mean, if I look at from the perspective of quantum theory, it has a description, that measurement, and that measurement is a specific measurement. So in any, I mean, it could be, I can imagine a strange theory where this is not possible and such measurement doesn't exist. I mean, so that is why I'm asking that, is there any theory-dependent argument? So
there is.
Alice,
maybe this is okay. Maybe this is a point that I could there's a poster by my colleague Ile Ying on, I think this is the topic of it. This is not actually work with me, but work with but I think Eric Cavalcanti, my colleague at Griffith, is on this poster about local friendliness in the context of generalized probabilistic theories. And so that there's still interesting things to say in that context. Is that what you're sort of getting at by talking about theories that are not quantum theories?
Yeah, so my question is a little bit different, but maybe we can discuss it maybe later. Okay.
Yeah, so I don't know. I mean, I guess I was concerned with, I was thinking very much in the same style as Bell's theorem, that we have metaphysical assumptions that we try to formulate as much as possible in a theory-independent way, but then we just want to know. The interesting thing is the fact that quantum theory predicts that the consequences of those metaphysical assumptions can be disproven in an experiment.
Yeah,
and so we're free to use as much of quantum theory as we like in making a prediction for how this experiment is going to turn out.
Okay. So I have one more short question.
We have actually some more requests. Okay. Maybe you continue later on, maybe separately with him.
Okay.
Okay.
Yeah, sure.
Okay. Thank you, Howard, and thank you, Devashish. So now I shall go to Manik. Manik, if you have some. Yeah.
Yeah. Thanks to both the speaker for nice talk. So I am Manik. Hi, Howard. My question is to you.
Hi, Manik. Yes.
Yeah. So question is more about little bit clarification. So Charlie did this measurement inside, and measurement means she obtained some classical outcome.
Well, that's right. I guess it depends on what context you're making that statement. If we say that, the assumptions of the theory. Okay, if by classical you mean absolutely real,
yes,
then yes. So the metaphysical assumption is that what you said is true. Okay, that quality makes a measurement and gets an absolutely real answer. There is not an assumption of the collapse of the wave function associated with that, because we're not mentioning quantum theory at all in the metaphysical assumptions.
So, but my next question is, Charlie obtained an outcome, and the Alice outside, she reversed the process.
Yes.
So now I'm saying, let's say Charlie, since outcome is classical, Charlie can make many copy of this outcome, and some outcome she throw outside unhidden to Alice. So I'm saying, when Alice is reversing the process, is it that the classical outcome is also erased?
Right. So what you're saying is, what if the information leaks out of Charlie's lab?
Yes.
So if the experimenters are careless enough to allow that to happen, then according to quantum theory, we would not expect a violation of the inequalities. So yes, so to make the experiment work, we want to avoid that to happen.
I see.
And that means that it must be the case that we shouldn't say there must be. Okay, if we believe that no signaling faster than light is possible, then it must be the case that no trace of Charlie's outcome can be known to Alice in the cases when she reverses, right? We're not making any particular statement that what that means about this outcome. It's like it comes into existence. Presumably it has to go out of existence as well, but we're not being specific about that. It has to be unknowable to Alice, okay? So maybe it goes out of existence, maybe it continues to exist, but just cannot be known to any human observer, and therefore there's no way they can exploit it to signal faster than light.
I see. Okay, that answers my question. Thank you.
Thank you, Manik. Thank you, Howard. So, Nicola, your name is on the list in case you have any other question. Okay, thank you. So maybe you place your question. You just go to that place. Yeah. Oh, yes, mic is there.
Hello, myself Nikhil from Azhar, Kolkata. So I have quick two questions. So first one is regarding the lifetime of superposition. So what is the difference of order? What is the time difference of order between classical superposition, lifetime of classical superposition and quantum superposition? Means just using that words vaguely. But
Yeah, so if we believe in we need a model to answer that question. In quantum theory, the superposition lifetime is infinite for everything, including for a table, because we believe in many worlds. In collapse models, we make a proposal to be tested by experiment that the superposition lifetime, let's say if your elementary particle like a proton or a neutron, it is 10 to the power 17 seconds, which is the order of the age of the universe, 10 billion years. It's a very large number. So it essentially never collapses. Now if you have an object made up of n particles, like a table, the collapse time becomes 10 to the power 17 divided by n. Yeah? So are you asking what is the collapse lifetime for a macroscopic object? Say it has 10 to the power 23 particles, then 10 to the 17 divided by 10 to the 23, which is a microsecond. So from the age of the universe, we have gone to a microsecond. The first number is not felt by human beings because very large. The second number is not felt by human beings because very small. But the physical consequences are dramatic. The proton stays in a superposition forever, and the table is never in superposition. This is a beautiful thinking on GRW's part, how they played with two large numbers to get to extreme results. That answers your question? Yeah.
another one, just in relation to this one only, I just need order. So like we are talking about collapse of many things, means wave functions. So what is the time order of this time scale at which this phenomena is happening?
How long does the collapse last?
Yeah. Means
the process of collapse from the start to the end.
Yes, sir.
That would be model dependent. Henrik, you want to say something?
Some rough order also works fine.
From the start of the collapse to the end of the collapse in a collapse model, how much time elapses? I think this would be model dependent. No, can you?
I don't know. It's model dependent, and I wouldn't be able to give a good answer.
Yeah. And we want it to be very tiny, right? Otherwise, we would see the wave function. We observe superposition and then end of no super. So at least less than the human perception time.
Is it less than the attoseconds, or is it?
Need not be that small. I mean, less than a microsecond would be good enough. It's not so. So I can raise a question for the audience. You raised a good point. What kind of an experiment should we do to see collapse of the wave function playing out in time? There is a superposition, there is no superposition. Even if quantum mechanics says this is instantaneous collapse, we don't believe in it. It should be some time scale. So collapse models, if you see the literature, will tell you how one branch grows as e to the tau or something, and the others fall as e to the minus tau. So for models, you can work out time scales. But what experiment to do to show that one branch of the superposition is growing and others are dying? I don't know. I have tried asking this to experimentalists. So if anybody, Howard, you want to say something? What experiment should one do to watch collapse? Or anybody else here?
Anyone? Howard, in case you have some answer,
yeah.
we cannot hear you.
No,
yeah, go ahead.
Yeah. Sorry, I've lost the thing again. But I think, yeah, it depends on which sort of collapse model one is talking about. I mean, it's fairly clear in the standard. Yeah, there are all sorts of ideas about how to test it in experiment, the sort of GRW style collapse models. but there are more exotic ones which could involve consciousness, even the non-Markovian ones, which I mentioned at the beginning that I'd done a little bit of work on. It gets much harder to know how to actually test those. Yeah.
Mm-hmm. Thank you.
Thank you, Howard. Professor Arun Pati.
Can I add something here?
Please.
Yeah, myself Arun Pati from Center for Quantum Engineering Research and Education at PCG Crest. Here. Yeah. So
yes, sir.
Yeah. So coming to your last question, so already people have done experiment where they try to measure the time of collapse. Not only they did that, they could also before the quantum state goes to the collapse, they could also retrace back to the original state. So that already been done by I don't remember the reference, but already few years back they did this experiment. Okay. So. Yeah.
Okay. Thank you very much, Arun.
And coming to your GRW model, also recent experiment they falsified it, right? So you might have seen that. So there is already experiment which falsified GRW model.
No.
So
Henrik, someone is saying GRW is falsified. Which experiment would that be? No, right?
Yeah, I can dig out later.
Not falsified. Yeah. No, it would make big news if GRW is falsified.
Well, I agree. I mean, my understanding is with the initial parameter values that were proposed, that has been ruled out. I think that's correct. But there's still
Adler's values, yes, but not GRW. We are still about 6 orders of magnitude from GRW values.
Really?
Yeah.
Okay.
So, Henrik, do you have any point to make on this? Okay.
Okay, thank you, yeah.
Thank you. And yes, so we have one more question from, yes. So please also mention your name and the affiliation.
Hello. Yeah, thank you. So my name is Aryaman from IIIT Hyderabad. So this is more of a general question from a computer science point of view. So we are asking many questions that result in either yes or no answers. So this we can call them as decision problems. But it turns out that some decision problems can be proven to be undecidable, like the halting problem. So similarly, how do we know that this universal quantum computer that Professor Howard talked about, whether it will halt with an answer? So what I'm trying to say is that some questions have yes or no answers, but we cannot build a definitive Turing machine that will solve those problems. So before we attempt to solve these decision problems, how do we know that they are solvable in the first place?
So your question is whether AI can reproduce human intelligence in some form?
Not just AI. So this is more of a general question. Okay. For example, just the problem of deciding whether we are a friend or we are the super being that is observing. That is also a decision problem that can be phrased. Or this is getting philosophical, but whether we actually live in a matrix or not.
Okay,
so
thank you.
That question about the friend is actually similar to this one. So how do we know that these are solvable in the first place?
Yes, so the question goes to Howard first, and then maybe some more comments from the audience. Howard, please.
Right. So I mean, there are philosophical questions that are challenging. I don't see, and which obviously have a role. I don't see how the questions about halting or whatever. It's not obvious to me what role this would play here, because at least the way I'm imagining it is that we already are at the stage that we have artificial intelligence that everybody accepts as being human level. And then it's just a question of taking that program and converting it into a program that would run on a quantum computer, and which has to be big enough and fast enough for that to work. So I don't know. I mean, it's not as if we're not asking the quantum computer to do anything that we wouldn't ask the AI running on a normal computer to do. You would just be like, okay, read this input and then tell us what you saw. That's literally, and maybe think about it and then tell us what you saw. I mean, that's literally all that's being asked here. So I don't see that there's any, formal sort of decision problem that we're asking the computer to solve. The problem about, and whether something is a super observer or not, as I said, I mean, I think that's just, we can do the experiment and see whether it works or not, and that will answer that question. Whether something is a friend, that's a qualitatively different sort of question. I think that's a philosophical question. Not to me, obviously, to do with computation, but but maybe I'm missing something. Obviously, Penrose thought that all of these things, uncomputability and collapse and gravity and all of these things were somehow linked together. But I don't see that that's necessary with the theorem.
Okay,
Hopefully that's some sort of answer.
Yeah, you have some comment to make, so please.
Yeah, myself Arun Pati again here. So I would like to add some of my thoughts in this context. So personally, I believe that even if you have advanced AI, that can never be equivalent to human AI or human intelligence. So you can call HI. Okay? So AI can never be able to match HI. Okay, that's first thing. Second thing, maybe if you have full-fledged quantum computer and you can develop quantum AI, and if nature is playing some role, in designing quantum consciousness or playing some role in quantum brain, maybe quantum AI can match human intelligence. Okay, that is my personal view.
So is it a belief or it's just, you have some logical assumption?
No, it is my personal view.
Okay. Is there any more? Yes. So I think this would be the last question, and after that we'll close. Dipankar, you also.
Hello. I am Orgho Das from IMSC. I am from statistical mechanics background, so very naive in this field. So I have a couple of questions. First one is to Professor Wiseman. So I'm just curious that what is happening to Bob when Charlie is measuring, or when Alice is reversing the measurement, what is happening at Bob's end within quantum theory?
Right. So Bob has the boring task of just in this version of just measuring a qubit in a basis of his choice. What's happening in quantum theory? Well, I guess that depends on which version of quantum theory you believe in. But if you believe that, for example, that humans cause collapse, then that would mean that when Bob makes his measurement, that the wave function should the entangled system, and that could include Charlie or Quali, would collapse as well. But of course that raises the question about when would that happen, because these are space-like separated events. So we can't say, the measurement takes place on Bob's side. When does that take place relative to Quali's measurement or Alice's measurement? In standard relativity theory, there is no matter of fact about that. I don't know. I thought that might be a helpful comment, but maybe that's just making things more confusing.
Yeah. Okay. So I'll think. And second question is to Professor, both of you, particularly Professor Singh. So in his model, he says that while the space-time we see is classical, so the idea is the collapse is happening all the time within your framework, so that we experience, or the existence is mostly classical. So I'm just curious that what happens to or whether in some approximation the unitary evolution is found. I mean, if it is collapsing all the time, then why the evolution is unitary at all?
So collapse is happening very rapidly for classical systems. So that is forced by a non-unitary evolution and keeping macroscopic things classical. But if you take a quantum object like an electron, with which you do a double slit experiment, it goes through presumably both the slits and you see interference. That means spontaneous collapse has not happened. It's very rare. It happens once in a very long time. and for all practical purposes, the electron's evolution is unitary.
Yes. No, I am saying in your trace dynamics, because the electron, this is moving through space-time, right? So, yeah, I'm just, I might have missed some point, but from your comments, it appears that within trace dynamics, the collapse is happening all the time.
No, trace dynamics should reproduce collapse models. In trace dynamics, collapse is being caused by an imaginary part of the total Hamiltonian. That imaginary part will be very small and negligible for the electron, so that collapse will be rare, and the imaginary part will become significant for a macroscopic object, so that collapse will become frequent. Trace dynamics is supposed to take care of the electron as well as the table, but into different limits. Does that help?
Yeah. Thanks. Yeah.
Thank you, Orko. Maybe, yes. So maybe, Guruda, you please go ahead.
Last question, no?
Okay. No, we have one more.
It's for Howard. So when Manik was telling that result is classical, then you are hesitating to tell it classical. But anyway, measurement result can be copied. In that sense, it can be. It is classical. But my question is slightly different. So I have not fully read, but I have seen some comments by Zukowski, and he has commented that pre-measurement has no result.
So he calls we're calling what Quali does a measurement or an observation, and he says no, that's not. It's a pre-measurement. So. So that's just adopting. So I would say that this is not a criticism of the theory. This is just saying, I reject this assumption. I think it's saying, Zukowski, he's just saying, for me, only humans have absolute observations or absolute thoughts or whatever, and anything that an AI on a quantum computer is doing does not have the same reality, right? So it is not as real as any thought of a human. So it's not pointing out some flaw in the theorem. It's just saying, for him, the assumption that he would reject is the assumption that we call friendliness.
Okay, thank you.
Harold has a comment on this, possibly. Yeah, please.
Hi, I would see Marek's comment a little differently, because, I mean, what you want Quali to do is to give a well-defined answer. I mean, he gets some particle in some superposition state or whatever, and he has to give a defined answer. And then the question is whether from this well-defined answer, which seems to me like modeling the collapse anyway, that from this well-defined answer you have to reverse everything. And the question to me is whether from a very well-defined result now already, we still can do this reversal.
Right. So this is, this is exactly why we proposed a specific experiment involving a quantum computer. And so well-defined is, well, Quali is as intelligent as a human. Quali thinks he's made an observation. Quali is able to communicate that result of that observation to us. If we choose to, we can open the envelope and find it out. Or we can still reverse all of those things. Okay, obviously it's not literally an envelope with a piece of paper in it. It's actually, it has to be, a quantum register with some quantum information in it. But still, we can choose to read it, or we can choose to send that information back into the quantum computer and run all the gates into reverse, and then according to standard quantum theory, all of that can be reversed. So if at some point you have to either bite the bullet and say, well, I don't believe that experiment is possible, in which case you're saying you don't believe that universal quantum computing is possible, or you just have to say, well, no, I just don't, Quali might be as intelligent as I am and, communicate to me as whatever, but I still don't believe that it's real. So then you're just rejecting friendliness. Those are the only options.
Okay, thank you. We have last question for this discussion session. Given that we are running out of time.
Okay. I shall I can discuss. Anyway, since Howard is online, So I just thought of mentioning that there was a long time back an example given by Albert and Wiseman that still remains valid today, that if you try to apply collapse model in the simple context of a fluorescent screen detecting the electrons but by emitting fluorescent photons, then the number of photons can be even very small, because a human eye can detect one photon or just a few photons. And the whole concept of collapse models hinges on this macroscopic distinction between the two states which are giving outcomes. This is one crucial. Another is the localization parameter, which fixes. But then you have a constraint on the localization parameter. You cannot make it too small. The separation between the heating would be very large. So the recent experimental tests also put some constraints on those heating rates. But what the worrying point is, and regarding which there have been some recent investigations, which may not be well known, that's why I wanted to mention, that Albert Wiseman example so raises a question for the collapse models, that when does the collapse occur? And this is only a small number, a human eye can detect. So 2010, Angelo Bassi did quite a seminal paper on EPR, European Physics Letters paper, where he analyzed the collapse model and applied it to the visual perception process with a collaboration with the physiologists who know the mechanism, the rhodopsin molecule. And that analysis has recently been revisited by Adrian also, but yesterday there was no time, so I did not bring it up. And recently Adrian has also written a paper on that. So the whole issue of collapse time came up. That I wanted to mention, there those Angelo Bassi and others had claimed that the collapse time is there, can be computed, and it is less than the human perception time. The best measurement of human perception time is now 100 milliseconds. So that imposes a strict constraint on the collapse model, because no matter what interpretation you use, ultimately it is, you have to observe, and one can fall back upon the observer, and then one can, of course, talk whether collapse occurs in brain or visual, but at least assuming that it occurs in the visual perception, and we know enough about its physiology. Now, brain we do not know much, so one can compute collapse time there. So that's an interesting result, but then Adrian has recently questioned that result, that calculation has to be improved, and so it is not clear whether it would satisfy that constraint that collapse time has to be necessarily less than the human perception time.
Yeah, for what I know of, in this context, Steve Adler also did similar calculations, so he's bound from such visual perception considerations. The lambda, the collapse rate parameter, should be, I think, around 10 to the minus 8, 10 to the minus 9 in that domain. That has been ruled out. But the GRW values 10 to the minus 16, 10 to the minus 17, what I understand from Henrik's talk is that we're still about 6 orders of magnitude from ruling out GRW. If 10 to the minus 17 per second lambda is ruled out, then we can give up, is my understanding.
Thank you very much.
Can I just make a comment?
Who's speaking? Where? Yes,
Sorry.
yes, Howard, please. Sorry.
Yeah, no, I just going to say that I completely agree with Professor Holm that, the most important thing that a collapse model would have to do is to account for a classical reality coming into being before the human, on a time scale shorter than the human perception time. And I think that does surprisingly put, I mean, I'm not an expert in this, but I think that does put a surprisingly strong constraints on the parameters in the Markovian collapse models that are being stressed, pressured by experiments. So, I just want to agree with that. The importance of those calculations and the relevance of them.
Thank you, Howard. There may be some more questions, but we want some question to be unanswered, so that we have motivations to meet again in some other occasion. So with this, we will close the discussion session, and I would like to thank our rapporteurs of this morning session, and also the engaging discussion we have about last 2 hours, almost. And with this, okay, thank you very much.
Yeah, now we have the motivation to come to India. Yeah, we'll give to,
you could give it to
one
my
of the students who is there.
Yeah. I have a student, Ingita Banerjee, also in the audience.
Can the student come here and take it? Yeah. On his behalf, his student is coming.
Thank you. Thank you.
Yeah, so now it's a photograph time, and then we'll have lunch. So please all meet at the lunch place. They are making some arrangement. Yeah? So we just all of us go for lunch.